Hi everyone, welcome back. I hope it was okay. Can I take a minute to get some feedback from you? How are you finding this, my speed and what I'm teaching you? Are you able to understand? Do you want me to go faster, slower? Anything you want to share with me?
Good evening, ma'am.
Yes?
Ma'am, I'm feeling it okay. Like the speed is okay.
Hmm.
Able to understand.
Right.
Yeah, so everything is okay.
Oh, that's good to know. Thank you for the positive feedback. But at any time, if you find I'm boring you or I should go faster or slower, please do let me know. You can interrupt and tell me. So let me start sharing my screen again. Where is my screen? There. Can you see it now?
Yes.
Okay, so yesterday I had announced that I'm going to move to a new topic today, but it turns out, so I was going to skip over two small results, which I'm confident by now you can do yourself. But it turns out, it seems there is a technical sort of result which you will need later in the other two sets of lecture. So I will do one of these results, and then we move to the next topic, which is the very important Rie's representation theorem. Okay, so this is really the last thing before we move to Rie's. Okay, and I hope, I mean, it's quite simple, so I'll go over this a bit quickly. So suppose mu x is finite and f is Lebesgue integrable. S is a closed subset in C, and that the averages okay, belong to S for every E. So what should E be? Quickly, just look at the statement. What condition should be put on E immediately? E should be measurable. What else?
Measure of E not equal to 0.
Yep, because we have a denominator term with mu E, so this should be greater than 0. So this is my hypothesis, and that's all. But it's not a weak hypothesis. You have this for every E which satisfies this condition, then fx must also be in S for almost all x in X. Okay, so let's prove this quickly. So we want to say that the set where fx is outside S has measure 0. Yeah. So what can we say about SC? This is open. Therefore, for each x, what do we have? I can find a radius, open ball of radius, say Rx, such that for each x in okay, x is a bad choice. For each z in C, okay, Now I'm going to make this claim, and I think you will know immediately why this is clear. And we can find A sub Z and R sub Z okay, not X, but Z, sorry. X, small x, we are denoting elements of capital X by. Okay. Can you see quickly why? Because Q is dense in R, any Z, where is Z? Z is in C, huh? So Z is of the form A plus IB, and A and B are real numbers. So you can approximate A and B by some rational number, and similarly for RZ. So this can always be done. Okay. And now, therefore, can we say right? Is that correct?
Yes.
So at most, how many, what could be the cardinality of such things we'll have? Countable, cross-countable, right? So countable. So how many can there be? These must be countable. So thus we can find a countable number of closed disks delta, say with center alpha and radius r, such that, okay, I'm writing N. SC is union. Okay. Now remember, what do we have to prove? That the set, the range of F is in S for almost all X in X. Okay. So I have to if E is delta N, then mu E is 0. En is 0. Do you agree? So if Fx is in SC for some X, then Fx must be in some delta N. Okay? Right? Is this clear, the statement, or do I need to write something here? Basically, what we have to show is, guys, are you with me? Please give me some indication. Have I lost?
Yes, ma'am.
Okay. You know, sometimes when I'm teaching my usual class, I go on speaking for 10 minutes and then I realize that, I've been logged out. So I don't want that to happen. So just say yes or no at least. So we need to show this set that I've written in the square bracket. The measure of this set is 0. Do you agree? Yes?
Yes, ma'am.
And this is just union over n of this set. Isn't it? Because so SC is this. We have said SC is this union. Okay? And what is this? This is nothing but, oops, sorry. This is nothing but union ENs. So if I can show that the measure of each En is 0, then the measure of the whole set here, this will be 0, isn't it?
Yes, ma'am.
Fine. Should we go ahead?
Yes, ma'am.
Okay. Suppose, if possible, for n, mu En is strictly positive. Okay. Then mod of A ENF minus alpha n. So delta n's are the closed disks with center alpha n and radius Rn. Okay. Remember what is AEN? AEN are the averages here. So AENF is integral over En of f with respect to mu divided by mu En. So I write this, and that's simply okay, I'm short of space, so let me write this mod minus alpha n, and that's just 1 over mu En mod integral over E f minus, yes, alpha n is a positive constant. No, it's not a positive constant, it is a complex scalar, okay? But this is fine. And this is less than equal to, by a property which I mentioned last time and in which I was trying to prove when does equality hold, the end of the lecture yesterday. Okay.
Okay, ma'am.
And where is fx? X has to be in En. Okay, so fx has to be in delta n. This is f. It's implicit, but if just to make things better here, we write fx. So fx is in this delta n closed disk, which has radius Rn, has center alpha n. So you know what this is, modulus is less than equal to. What is it less than equal to? Rn? Is that okay?
Yes, ma'am.
And that's just Rn. So this means AENF also belongs to delta n. And delta n's are definitely sitting inside SC. That's how we made them. This is a contradiction to hypothesis. Therefore, mu En must be 0 for empty n. And therefore, we get mu of that set X, which I wrote in the brackets here at the bottom, X such that fx belongs to SC. Is 0. Okay. And this is proved. So this was a sort of just one more application really. And there was one more result which I have put in your tutorial list, problem sheet. So you will see it there. Hopefully, please do it. Okay, so now I'm ready to move to the next part of this lecture, and that will be dedicated to the Rie's representation theorem. Before we move on, let me do a just quick recap. What have we done so far? Extended the definition of integral to complex valued functions. What else did we do? We have studied linearity of integral or this function. Yeah. What else have we done? We have studied other properties of the integral. We have talked about sets of measure zero and the notion of almost everywhere, isn't it? We have extended the notion of the definition of measurable functions, and we have defined what we mean by a complete measure. Okay, so with all this out of the picture now, let me talk about the Rie's representation theorem. Okay, so I don't have any evidence to authenticate this, but I seem to read that this mathematician Ries did a lot of put in a lot of work to be able to define the integral without taking recourse to measure theory. Okay, so that was his intention, and it's a bit ironic now because in this course we are going to use his or an extension of his original result to show the existence of the Lebesgue measure on R, on Rn, and maybe many other places. Okay, so I will take the time to state the Rie's representation theorem in its full generality. But for now, today, I will give you the statement of the original theorem by Ries, which was just on C01. Okay, and I'll try and give you a different proof for that also. And then we will see the general, actually it's called the Ries-Markov-Kakutani theorem, representation theorem. So we will see that in its full general, and it will be very important for you to remember it going forward from this set of lectures. Okay, so let's first talk about, and what does the Ries representation theorem do basically? It tries to connect the notion of a linear functional with the idea of an integral with respect to a measure. Okay, or maybe just connect the linear functional with an integral. Okay, so what is a linear functional first? Have you seen linear functionals in functional analysis? Have you?
Yes.
Yes, ma'am.
So let V be a vector space over K. K is either C or R. Okay. So what is a linear functional? By a linear functional
V2K.
on V, we mean a map. What should we call it? Okay, we'll call it like this throughout. Del from V to K such that there is linearity. What does linearity mean? Alpha F plus beta G is simply for all alpha beta in the scalar field and Fg in V. Okay, so we all understand this concept, right?
Yes, ma'am.
Okay, simple examples. Okay, since we will be working with C01, be the space. Okay, let me take the real space. F from 0, 1. Okay, only real valued continuous functions. Then we of course know that C01 is a vector space over what?
R.
Okay, can you give it a norm? We don't need it for the definition of linear function, but just, okay, we'll come to it later. Okay, is a vector space over R. So, and let me fix x naught. Okay, why? So let me make it closed. And let me define del simply by okay.
Okay.
So this will be a linear function. And also note that if f belonging to C01 is positive, meaning that is f is greater than or 0 for all x, then del naught f is greater than equal to 0. Okay, this is called, del naught is then called a positive linear function, and it will play a role, important role in what we are going to do. Okay, such del naught is called a positive linear function. Okay, can you just extend this definition? We could extend this. You could make it choose n points and define this. Okay, a general form would be, maybe I fix x naught, x1, xn, and alpha naught okay, maybe not x naught because then it will, so, and then you define do you think this will be a linear function?
Yes.
Yes. Okay. Now I will not say anything about the statement that I'm going to write here. If you have something, you can just, but you can revisit this later, okay? The point mass at x naught. Have you come across this measure? So here, mu of E is 0 if x naught is in E, not in E, and 1 otherwise, okay? So anyway, I don't want to say anything more about this for now. Let's move on. Okay, so these are examples. Also, you could, we have seen this. In fact, this itself is an example. If you take, can I take V to be L1 mu, where X, M, M mu is a measure space in the sense we have been working with, and we define L1 mu as the Lebesgue integrable functions. So we have seen that V is a vector space? Yes?
Yes, ma'am.
Yes.
C. And can you think of a del we can define?
We can measure to its measure.
Integral, you mean?
Okay. Yeah. Integral F d mu.
Yes? Because we know this is a finite thing, and then del is a linear function. Okay? All right. So much for some examples. I'm talking about the integrable ones because they are more relevant to what I'm going to do. Okay? Okay, now here is the statement of Rie's theorem in a very simple case. So as before, I mean, of course, I can take C01 to be a complex functions, but here I'm going to restrict it to real. Okay, and I give you a simple proof. And suppose del is a positive linear functional on C01. Then there exists a, okay, I don't want to go through the technical things right now because I will look at the general proof anyway. But so I'm putting this in brackets. Is unique monotone function alpha such that where the integral on the right hand side, do you recognize this integral from your undergraduate work, is to be taken in the sense of Riemann Stieltjes. Do you know that? Have you come across this, guys? Are you there?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Oof. It just went off. Just 1 minute. Oh gosh. Okay, I have to write this again. Just 2 minutes. Okay. And for uniqueness, alpha, we need alpha to be normalized monotone. That is simply means right continuous on open zero. Okay, this uniqueness part I will not spend time proving right now because everything will fall under a more general case. But this is quite a straightforward thing, no measures in that sense. This is just the Riemann-Stieltjes integral of f. I hope you remember what is the Riemann-Stieltjes integral. Do you?
Yes, ma'am.
What is it? Oops. How do you define it?
We need a monotone continuous function.
Or a function of bounded variation, right? Okay. Okay. Monotone function.
Then f is a function which is bounded and yes, only bounded. Then
Okay, let me do it for what we need. So we just need it for this setup. So we can take continuous on, say, AB or 0, 1 itself. And for any, if I take a partition P,
yes.
so this is very specific, but you will just recall that you have done this. And del P is mesh P. Okay. And then we define this limit. Del P going to 0, summation, oops, sorry, N, okay?
From alpha ti minus
Oh,
alpha.
yeah. Otherwise, this is just the Riemann one. You're right. Or beta rather. Thank you. And where is Ti dash? Some arbitrary choice in here. So this limit, if it exists, and it exists for such choices, and is denoted by, and is called the Riemann-Stieltjes integral of f. You take beta t to be t, you get the usual Riemann integral. Okay? Okay, so before we start the proof, I will need some element from some elements from function analysis. So just recall C01. What is the norm on this you usually take? There are many norms you can take, but we'll take the sup norm. What is it? Sup mod of yes? Do you know this?
Yes, ma'am.
Yes, ma'am.
Is a Banach space. Okay. And what is the Hahn-Banach theorem? What does it say? What is the statement of the Hahn-Banach theorem? Anybody remembers?
Yes.
Okay. let, what should we call it? Z norm be a norm space and Y a subspace of Z if F whatever scalar field is a linear functional that we have just defined, which is bounded with okay, I don't need to say it here. Then there exists an extension F tilde such that F tilde is linear bounded and okay, this should be Z and norm of F tilde is norm F. Yes? Is that okay?
Yes, ma'am.
Yes,
Do you
ma'am.
all remember? Okay. Well, what does bounded mean here? When is a linear functional from a norm space to things like to be bounded?
Mod of fx is less than equal to m times norm of x for all x in x.
Pardon me for mixing up. I shouldn't use all this. We should stick to this. And you please have a look. When we defined the linear functional, we did not demand any kind of boundedness. Okay. And in the Rie's theorem that I'm trying to prove for you just on C01, there is no explicit thing saying that the delta is a bounded linear function, it's just saying positive linear functional. Okay. It turns out a positive linear functional is bounded. A functional delta from Z norm to K is said to be bounded when if sup of is finite, right?
Yes, ma'am.
And we define this to be norm delta. Okay? In that case. Fine?
Yes, ma'am.
Okay. One more thing. Okay, let me do it as part of the theorem. So let's start proving the theorem. This is proof of which theorem? RRT for C01. Okay, what do we have? We have del from C01 2R is a positive linear function. This implies that del is actually bounded. Have you ever seen a proof of this? Okay, and let me give you a quick proof for this. So let F belong to, so this is just proving that why it is bounded. So F belongs to C01, and we know infinity norm of F is what? Sup mod Ft, T belongs to 01. So this means mod of Ft is less than equal to norm F infinity for every T, okay, in 01, of course. Now, we remember F we have taken even to be real here, but here I actually, this thing you can see for those of you who want to, this will follow even if F is not necessarily real valued. So this means minus agreed? Are you with me here?
Yes, ma'am.
And this I can rewrite in terms of just functions in this way. Fine.
Yes, ma'am.
So this is as if you are saying norm F infinity plus this function. So norm F infinity is a scalar multiplying a function plus minus F another function. This is, where is this term lying? Definitely in C01 is greater than equal to 0, isn't it? Fine.
Yes, ma'am.
Now we use positive linear functional. What does positive linear functional mean? This is positive. That is, if G is greater than 0, G in C01, then so two notions of positive here. G greater than equal to 0, G is a function. G greater than equal to 0 means every image point of G is non-negative. Delta G is greater than equal to 0. This is just a real number being positive. Okay. And when this happens, we say this linear functional is positive. We have seen this before. Okay. So now I apply this definition to this function norm F infinity 1 plus minus F. What do we get? So therefore, okay. And does this imply, do you agree that this means Yes,
Yes, ma'am.
Yes.
this is true for of f in C01. Okay, and you look at those of you who are forgotten what it means for a functional delta to be bounded. You need the sup of all this mod del f in C01, norm f infinity less than equal to 1 to be finite. Okay, so this means sup the norm we are using is infinity norm. What is this less than equal to? Come on, tell me.
Norm of f.
No, I am using this here.
Norm f times
But I am taking sup. I'm taking sup over all norm f infinity less than equal to 1. So I will simply get 1. Isn't it?
Yes.
So this implies is bounded. Is a bounded linear functional on C01. Okay. Now we have this space C01 with infinity norm. Okay, so we have this already and we're working with this. What if I write B01 to be simply this? And I give it, will this be a vector space? Will this be a vector space?
Yes.
Yes.
So B01 is a vector space with respect to pointwise addition and scalar multiplication over R, because I'm taking everything over R, could as well have taken over C, and then it would be. And what about this? Do you think this is a norm space?
Yes.
Fine.
Yes, ma'am.
Okay, so can you tell me what my next step should be? I have given you, I mean, you don't know how to get hold of alpha, of course, but logically, I gave you Hahn-Banach theorem. I have set this up. So what should be the next step? I have a bounded linear functional. I should write the whole thing on C01. C01 is a subspace of B01. Therefore, by the Hahn-Banach theorem, there exists an extension of delta which is bounded and linear. Okay, is that fine?
Yes, ma'am.
Yes, ma'am.
Okay. Now we need to define. So let me call this 1. And of course, it's an extension. So this has to happen. Okay. So now we have to get hold of alpha. It happens, I mean, for this particular case, we can get hold of alpha concretely. Okay. You understand chi 0x? You must have seen this. Do you know what this function is? We have seen it, yeah, when we were defining simple functions and all that.
Characteristic function.
Yes, this is just a characteristic function. Okay, but so now it's in B01, definitely. But we couldn't have said that it was in C01. So I needed somehow, so it's clear why we need a bigger space here if we need this thing to work. And do you agree with this? This is a function. It's greater than 0.
Yes.
Yes,
It will take only 2 values.
Only 2 values, 0 and 1.
Okay. And we set alpha of x to be is everything fine here? Am I allowed to do that?
Yes.
So this function, this functional is defined on B01. It's an extension of the original one, which was only defined on C01. So I couldn't have written del here. It's not on C01. It's not, and this chi is not in C01, but this is fine. Do you think alpha is monotone? Can you do it quickly? If x is less than y, what can you say about chi 0x minus chi 0y? What will this function be? What will this be? So you'll have to do 3-4 cases. 3 cases. T does not belong to so T is here. Yeah. Fine. What happens in the first case? Everything is 0.
0.
Here,
0.
this one.
-1.
-1.
So this is correct. Yeah.
Yes, ma'am.
Yes.
Therefore, Okay. Okay, this requires a bit of something more because I've only told you that a positive linear functional is bounded, and I got this this extension, but we don't know that this extension is positive or not. It's bounded, but does that mean it's positive? So I'll come back to this. All right, but for right now, I want you to assume that it is positive. Fine. Therefore, alpha y is greater than alpha x. Isn't it?
Yes.
So alpha is monotone. Okay. So this we have to still check. All right. Now, so I have an alpha in hand with respect to whether alpha is monotone or not. For now, I need to get my relation between the functional, this value at f, and that some Riemann Stieltjes limit with respect to alpha. Okay. So for that, I need to define okay. And I will show, so this is something similar. So if I apply my delta bar, you see I will get alpha j by n and alpha j minus 1 by n. So it's looking a bit similar to that limit, the Riemann Stieltjes limit that we needed. Where is it? Here. Something like that. We haven't reached there yet, but it will look similar. Okay. So I'll continue from here next time. Okay. So for now, you can assume this is positive and this is monotone, but I'll tell you later why. Okay. And then use FNs to construct a Riemann Stieltjes sum. Okay, I think I'll stop here, Dr. Shetty.
Okay.